And I really hope I'm right and all of you are wrong. Yikes. All right. Good morning. Happy Friday. This is the Friday before spring break, so no class next week. Um, so this is the last lesson of this unit, and then when we come back after spring break, we will have review on Monday, and your test will be on Tuesday and Wednesday, and then we'll starting Unit 5 on Thursday. How fun is that? All right. So Bellwork says a circle is divided into 16 equally sized sectors. Six are blue, three are yellow, and the rest are red. The area of the red sector is 45.56. Oops, I forgot my units. Inches squared, probably. What is the radius? Round to the nearest hundredths. Oh, actually, I have it on this page, so I don't know how it got cut off. All right, so the final answer is 4.99 inches. People in chat, a bunch of people do not agree with me. Nobody got the same answer I got. So let's see where I made my mistake, or where I didn't make my mistake. I guess we'll find out. All right, so this problem gives you um, the red area, which is 45.56. So that right there, since we have six blue, three yellow, the rest are red, and there's a total of 16 equally sized sectors. That means seven, right? Seven must be red. People in chat agree with me. Um, what's the question, Caitlin? There's my mistake. There's my mistake. Okay. Yes, the answer is not 4.99. This math is going to be all wrong. Thank you. That was my mistake. I obviously can't copy my own question down right. So, yikes. Let's this is actually should be at a 16, not 12. Whoops, that's going to change well a lot of stuff actually. All right, so a full rotation is 2 pi. Well, 7 out of the 16 are red. So that's why we multiply 7 over 16 times 2 pi. That will give us just the radians, the portion that is the red sectors. So 2 pi times 7 over 16, that's going to be 7 pi over 8. Everyone agree with me on that? All right. So going on, I'm going to fix my work all the way through. So people who got 5.76, you are probably correct. And I'm totally wrong. All right. So the area of the red is 45.56 inches squared. All right. So we're going to use this formula here. This is for the area of a sector. So the area is going to be 1/2 times your radius squared times your angle of that sector, trying to find the area of. So that is 7 pi over 8. So we're just going to plug the stuff in that we know. We know the area and we know the angle. I did not write that. This should be 7 pi over 8, not 6. Everyone doing good so far? All right. So next, all right. So 1/2 times 7 pi over 8 times radius squared. That's going to be 7 pi over 16, not 12. We want to multiply both sides by the inverse, so 16 over 7 pi. So again, I have to change my work. Then next, you also probably want to avoid multiplying those out right now, especially the pi part. You can do 16 times 45.56 in the numerator, and then in your denominator, put over 7 pi. Make sure when you do 16 times 45.56, you write down the entire decimal, however long it is. But we can just save it for the end. I think that'd be safer. So we'll do square root both sides. Again, I have to fix my work because I typed it wrong because I'm bad like that. Okay, so then from this step, everyone can type in the square root of 16 over 7 pi times 45.56. Then you hit enter, and you don't get that answer because I typed my work wrong. So we're just going to do that. Um, I think people said it was 5.76. Is that right? Yep. So, yep, R equals 5.76 inches. Okay, so that is the correct answer. All right, nice job catching my mistake at the very beginning.
Is there going to be a question like this on the part two test
There was one on your.
for the unit?
There was one on your. Probably not.
Probably not.
Yeah, I know there's one on yesterday's quiz. That's why I'm asking because I failed it twice. That question.
Well, there you go. Now you know how to approach it, right?
Better than I did yesterday.
Okay, that works, right? You won't have one of these on your TGA. I already went over all 3 problems from your TGA on previous bell works of this unit.
Okay, thank goodness.
Yep. So people watching this, you might want to watch previous lessons for sure because I went over every TGA problem in a bell work in some form. This problem was on yesterday's quiz. Well, one similar to it. So well, there you go. Any questions on this before we go on to the lesson? Okay, so this is 4.08 angular and linear velocities. This is a 1-day lesson. There's no day 1 or day 2. Well, I guess this is day 1 of 1, right? We're going to convert between angular and linear velocities. All right, we're being recorded. All right, definition of velocity. So velocity is simply a change of something with respect to a change in time. So that something does not have to be something in particular, but most often it changes with some. I'm sorry, it changes with time since well, time is always changing. Now that's something, so it could be usually it's distance, right? So the most common thing that we change in regard to time is distance, whether it's like miles per hour, feet per second, meters per second, inches per second. All right. So we are not going to distinguish between speed versus velocity. So I will use them interchangeably, but there is actually a difference between saying speed and velocity when talking about, let's say, like physics or, yeah, basically physics. But I'm going to use speed and velocity for just simplicity reasons. I'm going to mean the same thing, but though they are slightly different. If you're wondering, um, velocity is more like a vector based, speed is not. So, and we'll be talking about vectors next unit. So just prepare yourself. Dun, dun, dun. They're pretty neat. They're not hard. All right. So angular velocity and linear velocity. So talking about angular velocity. So angular velocity is the rate at which the angle changes, hence the name angular velocity. So it's about angle, the change of your angle over time. So that's something I talked about in regards to like something per time. Well, that something in this case is your angle. So as a result, the angular velocity formula becomes omega equals theta over time. So the omega symbol here, this is lowercase Greek letter omega. This means angular velocity. So whenever you see this, you should think, hey, that's the angle, the change of angle over time. Your theta, this is the angle. Again, it must be in radians. Super important. Don't make the mistake we made yesterday. So radians, and then t is well, some time, whether it's like hours, minutes, seconds, days. weeks, whatever. Uh, and this should be on your formula sheet that all of you downloaded, correct? Did I get this one on there? Okay. You know what? So far, I haven't missed any formulas. That's pretty good. I'm sure I was going to bound to miss something because there's so many this unit. All right, so linear velocity. Well, linear velocity is the rate of change in the linear displacement of an object with respect to time. The linear displacement of an object that moves in a circular point, well, is the arc length s. We learned about this earlier. This unit of the circle from the object's initial position to the terminal position. So changing from one place to another, like your speed in your car, your what's it called? Not your tach. Is it your tachometer? Your speedometer. That shows your miles per hour. That's considered a linear velocity. All right. To connect linear and angular velocity, we must remember some concepts from geometry. So remember, in your circle, one full revolution of your circle, your degrees or radians, is 2 pi. So one revolution is 2 pi. We all know this. We've used this concept before. All right. So looking at 2 pi r, what is this formula? What is 2 pi r from geometry? What is that formula? Circumference, yes. So when it says that one length of the circle is 2 pi r, so let me draw a tiny circle here because I don't have a whole lot of space. Let's see. All right. So I got this circle here, and then you have you have your radius, right? And then if you know your radius, you can find remember the circumference would be basically its sector length, right? But it's the full circle, right? So that is the length of the circle. So imagine us taking a piece of paper. I'll use my unit circle paper. And if you were to fold it fold it so it's end to end, and then I kind of show you down the middle, right? It makes a circle, right? And if we know the radius of the circle, you know the circumference. Well, if you were to cut that circle and you were to unwind it so it becomes a straight line, well, that is the length of the circle. So from point A to point B, well, that would be the length of the circle. And that's what this is talking about. Pretty neat so far, right, guys? All right. So formulas for velocity. So you have pointer out here. Three choices. Oh, actually, let me go back real quick. I forgot to explain one little thing on this page. So, have any of you seen this before? Maybe in science class? Yeah, this is just the distance, rate, time pyramid. It's an easy way. If you memorize this formula, you can say, oh, distance equals rate times time. Rate equals distance divided by time. Time equals distance divided by rate. Just a really easy way to kind of find all the combinations for distance, rate, time formulas. Sound familiar? All right. So, yeah, rate is distance divided by time. That formula. All right, going back forward. All right, so velocity, this little italicized V, this is the Greek letter nu, N-U, nu. So that's pretty easy, V for velocity, right? But it's the Greek letter nu. All right, so this is linear velocity formula is going to be your sector length divided by time. Well, because this is going to be the length of your sector, so that's your displacement, and then time, whatever it may be. We also know from earlier this unit that S is equal to radius times the angle. So I can just replace S, well, with this to create a new formula. So now if you don't know your sector length, but you know your radius and your angle, well, just use this formula, right? And then we also know from the previous few pages that, well, your angular velocity is equal to theta over time. So I can replace, what did I replace here? We've replaced angle, see the angle and the time here? Well, we replace angle theta divided by t, theta divided by t with omega. So this becomes omega, the r sticks, and then there's your v. So three ways to write your velocity formula. And you can use these without thinking of how we got there. Just there they are. All right, omega is angular velocity, v is your linear velocity, s is your arc length, r is radius, theta is your central angle in radians, and then t is time. Right. Doing good so far? So, oh, here's something funny. Uh, so there's a feature in Neuro that I enabled that allows me to see who's actually like tabbed into the Neuro and who's tabbed out as everyone quickly tabs back in, except one person, two people. Yeah. Yeah. So I can see who's like, listening, but not actually like paying attention. You know what I mean? Because you may hear me, but are you understanding me? I don't know. Anyway, example time. So everyone should be kind of tabbed back in. If you're tabbed out, I know who you are. See you, George. All right. Volunteer want to read this question for us. Emily, go for it.
A merry-go-round has a radius of 15 feet. You jump on and time how fast you are going. You time that you complete 2.5 revolutions in 30 seconds. How fast is your linear velocity? Give answer in terms of pi and rounded to the nearest tenth.
Good, good. So when you read one of these problems about angular or linear velocity, you need to ask yourself, do they want us to find, well, the angles per time, or the, well, distance per time? Well, this one says linear velocity, so I underlined it to really emphasize we should have some type of distance per time for our final answer. So we probably don't want to use this formula because remember omega is for angles, and we don't care about the angles per time. We care about linear, which is going to be, I think we're talking about, is it feet? Is that what it says? Yep, feet. We care about feet per time. And it's probably, this is in seconds. Yep. So probably feet per second is really what we want. Right. So, given this information, are we going to use the first, second, or third formula for velocity based on what we have? What do we think in chat? Sarah thinks the second one. A lot of seconds, maybe. Well, let's write down what we know. What is given to us? So, radius and time. We're given, write this down. We're given the radius, right, which is 15. We are given What else we given? We're given revs per 30 seconds, revolutions per. So we know that. Um, so revolutions in 30 seconds. All right. So if we're given revolutions, um, it says 2.5 revolutions in 30 seconds. So how can we use that without me giving it away too much? But we are going to use the second formula. One revolution is 2 pi. Okay. Yep. So time is 30 seconds. Radius is 15. So what about theta? How do I find theta? 2.5 is 5 pi. How did you find 5 pi? What was the math you used? To find your total angle, so in 30 seconds, we go around 2.5 times. How do I find the total revolutions in radians? Yeah, I believe it's 5 pi, but how did you get 5 pi? Close, Emily. I think yeah, there you go. Yep, 2 pi. Yep, 2.5. So it's going to be, remember, one revolution is 2 pi, right? And we go around 2.5 times. So we take 2 pi and times it by 2.5. And that gives us the total angle traveled. So we went around in 30 seconds, 5 pi. So that's one time, two times, and then a half, right? And that goes back to this page here that some people were not paying attention to. That's one revolution is 2 pi. One revolution is 2 pi radians. Coming back to here, well, it says 2.5 revolutions. Well, so we take 2.5 times it by 2 pi, and that's the total angle traveled. Good so far? All right, so then we just plug the stuff in. Now 15, I don't know why I wrote 2 pi times 2.5. I should have just wrote 5 pi because we did the math in the previous step. I don't know. We should just put 15 times 5 pi there, not what I have there. I'm going to change that in mine. There's no reason for me to put that. All right, and then everyone go ahead and type that stuff in and then hit enter and tell me what you get. Okay, so round to the nearest tenth, please. What it says nearest tenth. 7.9. What's your units? Feet per second. Yep. Feet per second. Because this is linear. This is linear displacement. Remember, when you're finding linear velocity, you will never have radians for your units. It'll always be something per, well, feet, miles, meters, whatever, per, in this case, second. All right. So 7.9. Yep. All right. Everyone good? Any questions on this? Any questions? If you do, please speak up. If not, go to the next one. All right. So this one, who wants to read this to us? All right, Sarah, go for it. Julie, you can read the next one.
Okay, can you hear me okay?
Yep.
Okay. A runner is practicing on a 400-meter circular track. As he practices for a race, he keeps checking his time. Why though? He was able to complete a mile, 1,600 meters, in 6 minutes. What was his angular velocity around the track? Give answer in respect to minutes and then seconds.
Good. So this is going to be, I emphasized angular velocity. So we know right away our units is going to be radians per something. That something it wants radians per minutes, and we also want to write it as radians per second. So I want two answers for this one: radians per minutes and radians per seconds. All right, everyone, give this problem a shot. I'll give all of you, I think, 2 minutes will be good for a good start. 2 minutes. I kind of gave this answer away by showing omega, huh? Because you only actually have one choice for that formula. Whoops. But really, me underlining angular velocity kind of gave it away too. Right. So we obviously use the angular velocity formula. what does theta equal? Right in chat. What did you put for theta? So somebody said 8 pi, pi over 4. What else we got? Anybody who was brave enough to put their two guesses or want to explain how you came to those values? Well, let's. Yeah, no one's brave enough. Let's take a look at this problem and figure out what is the theta. So this one says, again, a runner is running around a 400-meter circular track. Okay. Let's see. As he practices for a race, he keeps checking his time. He was able to complete a mile in 6 minutes. Okay. So 1,600 meters. So it's telling us we have in 6 minutes he was able to do 1,600 meters. Right. So how many revolutions is that? 4. Yeah, can everyone see that? We take the revolutions would be, well, 1,600 divided by 400. So we know he ran around the track 4 times, right? So that's correct. So we know the revolutions. Now, how do I find the actual theta, the actual angle traveled? And Caitlin says it's 4 times 2 pi, and she is correct. Remember, because one revolution is 2 pi. We ran around 4 times, so 4 times 2 pi is 8 pi. So he traveled 8 pi. Angle theta is 8 pi. That's correct. Oh, I have a feeling I mistyped this one too. Your angle is not. Uh, your angle is going to be times 4 equals 8 pi. I know. That means I have to change my work throughout this entire problem. Or maybe I did it in the next step. I don't remember. Let's see. So, oh, I didn't change it. Look at that. So all this work's going to be wrong. Right. So let me just black out everything. Yep. I'm going to black out everything. This is all not good. Hang on 1 second. I think this is black. Let's take a look. Antonio beat me to it. Okay. I fixed it. All right. So we're going to have 8 pi. Then 8 over 6 reduces down to 4/3. So angular velocity is 4 pi over 3. And this is radians. I'll just put radians per.
I have a quick question.
Yep.
Couldn't you just multiply your final answers by 4 to get the same thing?
Yes, I could have. But I would say
Okay.
that's probably not the best way to get to your answer of fixing your mistake with. I wouldn't call it a mistake, but maybe not the best use of math in that problem. If you did it that way. Does that make
Okay.
sense?
Yeah, thank you.
All right, so 4 pi radians per minute. So we gave that answer, right? Now, I think in chemistry you learned about I think it's called stoichiometry. Does that sound right? Yeah, stoichiometry. So we have to convert radians per minute to radians per second. Yeah. All right. So I want to get rid of minutes and I want seconds, right? I want to get rid of minutes. Right. So how many seconds are in a minute? 1 minute, 60 seconds. So in 1 minute, there's 60 seconds. So this means that I can cross out minutes and minutes. This is how stoichiometry works, right? This is the whole point here. So now we are going to have 4 pi times 1 is going to be 4 pi. On the bottom, we have 3 times 60, 6, 12, 18. Ooh, I can actually reduce this. Well, I'm going to reduce this. Let me back up a second. And you don't have to do what I'm about to do in terms of reducing now. But look at that 4 and that 60. I can reduce both of those. So 4 goes into 4 once, and then 4 goes into 60. What is it? 15 times? 3. Yeah, it's 15. Yeah, it's 15. I don't know why I'm having trouble with that. Everyone agree with that? It's 15? Okay, good. Yeah, so I just reduced the 4 and the 60 to get 15. So now I can do, you're going to have 1 pi on top. And then on the bottom, you're going to have 3 times 15, 15, 30, 45. And now our units is radians per second. And let's convert these two answers into decimals. So everyone type in 4 pi divided by 3. Let's round to um, the nearest tenth. It doesn't say to do that, but let's go ahead and do the nearest tenth just because we did that for the last problem. So 4.2. So it's going to be about 4.2 radians per minute. And then everyone type in pi divided by 45, and what's our decimal value to one place? Zero point 0.1. 0.1 radians per second. Right, so we gave the exact form and the rounded decimal form for both of them. The problem wanted both. We wanted minutes and seconds. So we came up with 4 pi. Hold on, my pointer's messed up. Go. We had 4 pi over 3 radians per minute. Decimal converted is 4.2 radians per minute. Converting this into radians per second, we came up with pi over 45 radians per second. Decimal, it's 0.1 radians per second. Good. Everyone agree with those answers? All right, all right. I have 2 more examples. Let's try to go through this. This problem wants us to find linear velocity. Julia, you want to read this one for us? Julia tabbed out. See the icon says she's not here. Who wants to read this one? I think Julia fell asleep on her keyboard. Who wants to read this for us? Oh, okay. Okay. Who wants to read this to us? Julia?
Testing, can you hear me?
Yes.
Is the background noise too bad?
Nope.
Okay. A runner is practicing on a 400-meter circular track. As he practices for a race, he keeps checking his time. He was able to complete a mile, about 1,600 meters, in 6 minutes. What is his linear velocity around the track? Give answer in respect to minutes and then seconds.
That problem sounds so familiar. Well, because it's the same one as the previous page, but now you're finding linear velocity instead of angular velocity. Look at that. All right. And my guess is this problem is this problem should be messed up like last one. Hopefully I didn't make a mistake. All right. So you have to decide what we're going to use, first, second, or third formula. Let me see. All right. Which formula do you guys want to use? The first or second or third? Michaela, if you message me on Skype real quick, I'll drop it in for you. It's also on the course content page. Yeah, that was so our bell work for our first lesson of this unit says go to the OHS and download the formula sheet. All right, are we going to use the first, second, or third formula for velocity? The first one. I agree with you, Sarah. We use the first one. Because we know the sector length and we also know the time. Oh man, I messed this problem up again. Because in 6 minutes, he ran 1,600 meters. So the sector length here is actually going to be 1,600 and not 400. Whoops, messed that one up again. No, oof. I am on a roll. You are right. So we have to fix that too. Oh boy. Let me black this out as well. Okay, let's fix this problem. So he traveled 1,600. That is your sector length. So because he went around 4 times, right? So it's 1,600 meters in 6 minutes. All right. What's 1,600 divided by 6? Give me the reduced fraction first. 6, 12. So it's going to be like 200, 654, 400, 250 something. Oh, 800? 800 over 3, is that right?
I just divided both by 2.
You're right. I was giving the decimal answer, and I even told you guys give me the reduced fraction. So silly sometimes. Don't know what's going on. Okay.
You need the break, definitely.
I know 800 over 3, and this is going to be what's the units? What per what? What's our units? Minutes or meters per minute. It is meters per minute because remember the 1600 that's meters. R6 is the minutes, so this is meters per minute. Okay, and then let's go ahead and give the decimal equivalent. What's 800 divided by 3? Decimal. Give me nearest tenth. 266.7. All right. Looks like more than one person says that, so I will agree with you. 266.7. And that's meters per minute. Okay. Because we wanted in respect to minutes and respect to seconds. So stoichiometry again, we want to get rid of our minutes in place of seconds. We know from the previous page that in 1 minute, there is a total of 60 seconds. Whoops, that is not a 60. Right. All right, we can reduce like last problem. 860. How does that reduce? 800 over 60. What does that become? 80 over 6. So 40 over 3. Does that sound right? Yep. Let me give the link to the. Some people have to leave, and that's fine. Let me give the link. At the leave, there's a link to the slides. Warning, there's mistakes on it, of course. Right, so I'm just going to reduce 860, and I think it was 40 over 3 is what I did in my head, so hopefully it's right. Then 40 times 1 is 40. Over 3 times 3 is 9. That's 40 over 9, and that's minutes per seconds. And then what is 40 divided by 9? $4.4. That's minutes per seconds. Right. All right, we gave both answers and we're good. Oh, minute. I meant what did I do? Oops. No one corrected me. Minutes and minutes cancel out. We're left with meters on top, not minutes. Thank you. Meters per second, not minutes per second. That's just weird. Right. So this last problem, I'll save it for bell work on Monday after spring break. There it is. Feel free to work it out before then. And just final thoughts, I just want to just reiterate is when talking about linear and angular velocities, so angular deals with the radians per time. Linear velocity deals with some distant unit, for example, feet over time, so feet per seconds in this case. So just remember that. Um, when doing angular velocity, we don't care about the distance. It could be a mile, it could be 400 meters. It doesn't matter. We care about the revolutions, the radians when talking about angular. So in word problems, really read it and maybe circle, highlight, write down. It's talking about either angular or linear because it makes a big difference on which formula that you will choose to use. So there's my final thought for you. All right, guys. Well, thanks for coming. And as always, I hope you learned something.